Hi everyone. So today I'm just going to be talking about modal logic and correspondence theory, what modal logic is, as well as one cute little proof in the correspondence theory that I just think is fun. I'll be using red to denote expressions inside of the logic that we're studying, and blue for the expressions in our meta language, regular old mathematics. So in a formal logic, we'll usually have a list of atomic propositions, which are just purely formal symbols with no truth value associated to them, as well as inductive rules for building formulas up from subformulas, including from those atomic propositions, as well as axioms and deductive rules and a whole bunch of other stuff. Now, on the semantic side of things, when we want to build a model of our theory, the first thing we have to do is provide a valuation for each of those atomic propositions. So, for example, we might say that P is true, that R is false, and that Q is true even only of the Riemann hypothesis. And the interesting thing to take away from this really is that what we're doing is we're relating expressions within our formal language to statements in regular old mathematics. So once we've associated values to each of the atomic propositions, we can also do it to formulas in the regular way that you might expect, where, for example, phi and gamma is true, even only if phi is true and gamma is true. So what about in modal logic? In modal logic, we have the same regular formulas that you're used to in classical propositional logic. That is, no universal or existential quantifier, but everything else that you know. But we have two new unary operators, box and diamond. So we can have expressions like this one. But what do they mean? So if we were in a philosophy class right now, we would probably read box phi as phi is necessary, and diamond phi as phi is possible. But we're mathematicians, and we've already talked about the formalism for this a bit. How do we formally interpret these in terms of other expressions in our meta language? Well, thanks to Saul Kripke, we have something called the Kripke semantics, which is about as natural a way of thinking about modal logic as Boolean algebras or truth tables are about classical logic. A Kripke frame consists of a set of possible worlds W and a binary relation on those worlds, which you can basically just think of as a directed graph. Now, in classical logic, we gave each atomic proposition a value, but in modal logic, we want to give each atomic proposition a different value potentially at each world. We also now need new rules for interpreting box and diamond. So, suppose we have one of these directed graphs. The first thing we want to do is associate a truth value to each atomic proposition at each world, which we can think of as putting a little truth table in each world, something like this. Now, this is really cumbersome to draw, so usually we'll write it like this, where we just list the true atomic propositions in each world. Each formula will also take different values at each world, and this happens pretty much exactly how you'd expect. Since P and R are both true in our first world, we should also expect P and R to be true in that world. Trivial things will also be true, for example, so Q implies Q, and P or not P is true. This sets us up with enough machinery to be able to talk about our box and diamond modal operators. In which worlds will box R be true? Well, the answer is that box R will be true in a world if R is true in all of the worlds it points at. So, for example, since R is true in the second world, and it's the only world that the first world points at, then box R will be true in the first world. Furthermore, since the world on the right doesn't point at any worlds, it vacuously satisfies the condition that R is true in all the worlds it points at, so box R is also true there, and indeed, so is box of any proposition. Now, what about diamond R? Diamond R will be true in a world if there exists a world it points at which satisfies R. So, for example, since the middle world points to itself and it satisfies R, then it also satisfies diamond R. By comparison, this world does not satisfy box R. Now, you might notice here that diamond has a bit of an existential flavor to it and box has a bit of a universal flavor to it, and indeed, they're dual in a kind of De Morgan way. In classical logic, an axiom is a formula which will be true in every possible valuation, so for any different consistent way that you can fill out a truth table. In modal logic, the same is true, but now it has to be true in every world of every model. It turns out adding an axiom like this can put some constraints on what our directed graphs have to look like. For example, if I tell you that all formulas of the shape box P implies P have to be true in my logic, what can you tell me about any directed graphs which are able to model my logic? So the answer is, they're reflexive. How cool's that? And it's an even only if. Let's prove the forwards direction. So suppose we have an arbitrary Kripke frame satisfying box P implies P. Let's let W be an arbitrary world, and Q be an arbitrary one of our atomic propositions. Now, since our Kripke frame satisfies box P implies P, it should do so for every possible valuation. Let's make up a valuation right now. We're going to make a valuation such that Q will be true in a world X, even only if W points to X along our relation R. From this, we can conclude that box Q will be true at W. By definition, we said that box Q will be true at a world W, even only if, for all worlds that W points at, Q will be true there. But by assumption, box Q implies Q should be true in every world under every valuation, so in particular it should be true here at W, but we already have that box Q is true at W, so by modus ponens, Q should be true at W. But what does that mean? Well, just from definition above, it means that W points to W, and hey, we've proven that W is reflexive for an arbitrary world W. And the other direction of the proof is completely trivial, so congratulations, you've just done your first very easy proof in modal correspondence theory. There are some great general theorems in correspondence theory, where if you have an axiom shape satisfying certain properties, you can computably determine the frame condition that it corresponds to. You might ask, what sorts of frame conditions we're able to correspond to? And it turns out that you can't encode every first-order frame condition. That is, a frame condition expressible within first-order logic. But you can encode some second-order frame conditions. This is interesting because second-order logic is more expressive than first-order logic, but is also less tractable to work with. This puts the correspondence theory for modal logic in an interesting position, where we get some of the expressiveness of second-order logic without all of the difficulty. An example of some first-order frame conditions that we can't encode are irreflexivity and antisymmetry. And the prototypical example of a second-order frame condition that we can encode is that the Gödel-Loeb axiom captures the condition that R is transitive and well-founded. This last axiom is particularly interesting because if you add it to your system, you get the Gödel-Loeb provability logic, in which the box operator is interpreted as the statement that something is provable in any system containing piano arithmetic, which is a fantastic story for another day that I can't get into now. This was only the most vanilla flavor of modal logic, with a single modality box and its dual diamond. In general, there may be many such modalities all interacting. For example, different colored boxes and diamonds corresponding to different colored graph edges. And the correspondence theory for more exotic multimodal logics isn't as well explored. In some cases, it doesn't even make sense until you generalize the question a bit. So that was my talk. Thank you for watching. I hope you enjoyed it. I hope it was within 7 minutes.